So we're going to look at another optimization problem, and we're going to use this example, and I'll go over what we're going to do on this example. So we've got a sheet of cardboard measuring 80 centimeters by 60 centimeters, and it is used to make an open box. So we're trying to find the maximum volume possible using this cardboard sheet. So we're trying to make a box, an open box. So if we think about it, we have to use our creative skills. So I've got a diagram. It's always important we draw a diagram. It's probably makes solving the problem so much easier when you can visually see what's happening. So what happens is we've got a cardboard sheet, all right, measuring 80 by 60, and we're going to use this to make our open box. So if you remember some of your artistic skills, you normally have some of these corners that we have to cut off, all right? Well, we cut off and we fold in to make our cardboard box, right? If you think about this, these cut off corners, whoops, you can tell I'm not an art teacher, I can't draw straight lines. These corners are just 8 by 8 corners, not 8 by 8, X by X corners, right? Because if you think about it, when you cut that out, that becomes the height, right? So we're trying to make a box that looks a bit like this. I'll try my best to draw it as best as possible. Something along the lines of that. Right, and it's open, so we can see the inside. So that's what it's like. So this X over here is the X right there, right? So what happens is if we think about we're cutting off those corners, we're going to fold it up. Our length, so if here this is 80 centimeters, our new length would become 80 minus X minus X, because we're cutting off two X's over there. So that becomes 80 minus 2X. So that is our length. And we do the exact same with our width. So our width, we're cutting off the X's over there, becomes 60 minus 2X. So over here, I'll write down, we've got 60 minus 2X, and this is 80 minus 2X. And now we're going to find the volume. Right, so if you think about a volume of a rectangular box, right, the formula we get, the general formula is V equals length times width times height. Okay, we know what our length is. Our length is 80 minus 2X. Our width is 60 minus 2X. And our height is X, right? So we're going to substitute this into our volume formula. So V equals length, which is 80 minus 2X, width, which is 60 minus 2X, multiplied by height, which is just X. And now we're just going to expand this out, because when you expand it out and put into this expanded expression, it's easier to differentiate. All right? So we get 80 times 60, well, 8 times 6 is 48, so that becomes 4,800. We got 80 times negative 2x, that's negative 160x. We've got negative 2 times 60, that's negative 120x. And we've got negative 2x times negative 2x, that's positive 4x squared. We've still got the x outside. So we can simplify that. We get 4,800 minus 280x plus 4x squared, all in brackets multiplied by x. Now I'll multiply the x inside. So V equals 4,800x minus 280x squared plus 4x cubed. All right, now we've got our function, and again we're trying to find the maximum volume, so we're trying to differentiate and make that gradient function equal to 0. So remember, we're going to find dv dx, and we want dv dx to equal 0 to find our maximum x value that gives us our maximum volume. All right, so let's go differentiate this. So dv over dx, well, that equals 4,800 minus 280 times 2, that is 560x plus 12x squared. All right. Now what you could do over here is, because we're going to make this equal to 0, so I'll go 0 equals 4,800 minus 560x plus 12x squared. Now what you could do is, it's a big expression, I could try and take out common factors, but we've got a graphics calculator, so we might as well use it. So I'll bring that out. Cool. So go into our polynomial equation, polynomial degrees 2, and we substitute our value. So we've got for x squared, the a value is 12, negative 560, and positive 4,800. Now we get two values. We got 35.35. Oh, and I'll go down. Oops. 11.31. So I'll write these down over here. So x equals 35.35 or x equals 11.31. Now we need to determine out of these two which one is our maximum. So what I'll do is you can do either one, either the second derivative test, the gradient test, or you can just do a graph. All right, and draw it up and see what it is. I'll do the second derivative test. So I'll differentiate this function over here again. Oops, I was supposed to highlight that. I'll differentiate that function again. Okay, so I'll have the second derivative of the function. We get negative 560 because the x drops out, plus 24x. And now what I'll do is I'll substitute in each x value to see what I get as my second derivative. So I'll substitute in the 35.35 first. So I've got d squared v equals dx squared. Oh, no, d squared v over dx squared. Negative 560 plus 24 multiplied by 35.35. So you notice I've rounded this to 2dp. The more decimal places, the better. Just for this example, I'll go to 2dp. It's easier. I'll go to my calculator and I'll write it down. So I've got negative 560 plus 24 times 35.35. We get 288. 288.4. Okay, so now this is obviously greater than 0, so if you remember, since it's greater than 0, this is our minimum. But let's go and do the second one anyway and test it out, just to be sure it's our maximum. So d squared v over dx squared equals negative 560 plus 24 multiplied by 11.31. Go back to my calculator. I've got negative 560 plus 24 times 11.31. We get negative 288.56. Negative 288.56. So therefore, d squared v over dx squared is less than 0. Therefore, this is our maximum. So we're going to use 11.31 as x and substitute in to find our maximum volume. All right. So I'll go back to my volume function if I remember it. Where is it gone? I'll just cut this out. You can choose either one. You can choose either the bracket version or the expanded version, whatever one you prefer, and you're just going to substitute in. So I'll bring it down here. And I'll paste that in there. Cool. So we're going to substitute in when x equals 11.31 to find our maximum volume. All right. Just remember the units. Remember, I always forget my units. I'll go back to the top. Units with centimeters. So I have to remember that. So that means we're going to have centimeters cubed. So V equals 4,800 times 11.31 minus 280 bracket 11.31 squared plus 4 bracket 11.31 cubed. And I'll go to my calculator because again, it's not nice numbers, so I'll use it anyway. 4,800 bracket 11.31 minus 280 bracket 11.31 squared plus 4 bracket 11.31 to the power of 3. So make sure you put those brackets correctly so you get the right value. If you want, sometimes it's good to do each bit at a time just to be safe. I'm just going to do all of it together because I'm pretty sure I've got my brackets correct. So I've got 24,258.42, I'll round it to 2 dp, centimeters cubed. So just remember that, 24,258. So V equals 24,000, oh I forgot already, 258.42 centimeters cubed. And this is our maximum volume. Okay, if you want, you can give the dimensions now. So if you go back to what your length, width, and height was, so we had length equals 80 minus 2x, width was 60 minus 2x, and height equals x. We can find out what our dimensions were as well by substituting it in. So we've got 80 minus 2 times 11.31 for length, which equal, and I'll put it into my calculator, 80 minus 2 times 11.31, 57.38. So 57.38 centimeters was my length. My height, my width was 60 minus 2 times 11.31. Put that in my calculator as well. 60 minus 2 times 11.31. We get 37.38. So 37.38 centimeters, and my height was 11.31 centimeters because that's what we found for x and height equaled x. So that's how we go through to find our maximum volume, or using optimization, going through that process. So it's just going through that process of differentiating, making your gradient function equal to 0, finding the values of x or whatever the variable was, determining what your maximum or minimum is, and then using whichever one to determine your maximum or minimum volume. And that's the process we go through to solve this problem.